Morning, everybody. It's Jeff Copperthite, E-Systems Engineering. We're going to go through a couple of force problems today, and we're going to take a look at sort of the components and systems that are involved in finding the answers to these kinds of questions. So in a force problem, you're basically trying to figure out what is the net force on an object in the diagram. So basically, we're kind of taking a step further and going right from free body diagrams directly to finding out what the actual retail net force is in a problem. So in this situation, we're going to take a look, start with this situation right here. This problem is from your PowerPoint that's on 214 in the PLTW resources page. So if you want to check out that and see another alternative way to look at this problem, you will find it there. We're going to go through this step by step and kind of understand what is entailed with finding the answers to these questions. So here's the situation. We've got a boat being pulled by two people, and they're pulling with the same magnitude. One person is pulling with 75 pounds of force at an angle that's 35 degrees above the horizontal. And then you got a second person who's pulling with the same magnitude, 75 pounds, but pulling with at 35 degrees below the horizontal. So you have this kind of going on here. And our question here is finding out what is the resulting force that you would get on this boat with these two people combined. Okay. Now here's a question for you. Do you think it's 150 pounds? What do you think? Do you think it's 150 pounds? It's something to think about. By pulling on an angle like this, do you think that they're going to be pulling with a net force of less than 150 or more than 150? It'll be less than. Good. Okay, so we understand that right away just by kind of recognizing that when they're pulling on an angle, their resulting forces are not going to be as magnified in the horizontal or rightward direction in this problem because of the angles they're pulling at, right? So it will be greater than 75 as we can tell, or most likely greater than 75 as we can tell, but it will definitely be less than 150. So that's a good kind of check mark right here, because we end up with an answer that's greater than 150 that already tells us that we did something wrong. So before we kind of tackle this problem, let's take a look at a couple of reminders about vectors. Okay, so let's go to the next page here, and we have a reminder on our trigonometry with forces. So let's say we had a force like this one. We could actually take that first force and we'll kind of throw this in here. So let's say this was 35 degrees right here, right? There's our 35 degrees. I'm drawing with the mouse, so bear with me. So that's 35 degrees. And the hypotenuse is the force vector, right? So in this case, this person is pulling with a force of 75 pounds. Well, we always can think about that anytime you're pulling on an angle, some part of your force is directed horizontally, and some part of your force is directed vertically. Okay? And it's based on the same idea behind right triangle trigonometry. The angle in this case will change how much of this force gets applied horizontally and gets applied vertically. Just from the visual, which of these two values is going to be higher? Do you think the x is going to be higher, or do you think the y is going to be higher? What do you think? Okay, if you said or were thinking the x, you are correct. Okay, two reasons for that. Number one, it is drawn bigger, right? This component vector is longer than this component vector. Also, another thing to think about is the size of the angle. If the angle is less than 45 degrees, that means the adjacent component is going to be greater, okay? If the angle, and I'll write that down, if angle is less than 45, then the adjacent component will be larger, okay? So when we calculate these, we're going to find that the x component, f sub x, is going to be greater than the y component, f sub y. So another thing to look at in this diagram is the way that this is set up is exactly the same as any other SOHCAHTOA right triangle trigonometry problem that you've done in the past. So if you're comfortable in solving right triangles, then you will also be comfortable in finding components of force vectors or any other vector for that matter. So let's take a look at how to do that. Now, in my class from Tuesday with the same class that we're recording today, we did conclude the class with looking at component vectors, but we also said that we would take some time and kind of look at it again today. So here is the setup. We have the force vector F. That's the hypotenuse. The adjacent side is going to be our F sub x, or our x component, and the opposite side is going to be our y component, or our F sub y. So if I wanted to set up a trig ratio, I can set up the following trig ratios. If I have this as my reference angle, and I wanted to use sine, I can say the sine of this reference angle is equal to the opposite side over the hypotenuse, right? So that's this one right here, okay? The sine of this angle is equal to the F sub y over the F, the opposite over the hypotenuse. Now, because I have the value of F, I can simplify this and solve for F sub y by multiplying both sides by F. And that means that F sub y is equal to the force itself times the sine of the angle, right? Let's get my calculator open here real fast. And if I were to do that, in this case, if I did 75, because that was the value of the force vector, and I multiply it by the, was it 35 degrees, right? Yeah. And I do the sine of that, and then hit enter, that tells me that the y component of this force is 43 pounds, right? So we're going to keep that in mind. We're going to be using that in just a second. But yeah, it's 43 pounds here. Now, if we do the same thing for the x component, well, the x component is adjacent, right? So if we did the cosine here of this angle, that would be the adjacent side over the hypotenuse right here. So that's that. Oops, let's try that. All right. That's that. It's the F sub x over the F. So the x component over the F. And the same thing here. If I want to get the x component by itself, I can just multiply F on both sides. And that tells me that to get the x component, I just need to do the force times the cosine of the angle. So same deal, 75 times 35, and then do the cosine of that, and hit enter, or equal, I would get 61.4. Okay, so the x component in this case is 61.4. We'll go with the 10th decimal place. That's fine. 61.4 pounds. Okay, so we found, of course, that the x component is larger and the y component is smaller than the x component. But notice that both components are less than 75 pounds. Okay, does anybody have any questions at this point? We're just looking at asking my live audience at this point. Any questions on that? You guys understand that? Okay, if you have a question and you're watching this video, please leave a comment below with your question if you're confused on how to do components. But we are going to look at these problems and use the components, of course, to answer the questions. All right, so we found those components to be 61.4 and 43 pounds. Now let's go ahead and look back at the problem. So here's the problem. They're pulling both same magnitude, and I'm going to just make a note of those. F sub x ones, F sub x equals, oops, 61, oops, that subscript hit it there, equals 61.4 pounds, and F sub y was 43 pounds, right? Yeah. Okay. All right, and of course I should probably label the units as well. Okay. So we found that to be the force here for F sub, for the first force, point A, right? So the x component was 61.4, y component was this. Look at force B real fast. That's also a 35-degree angle. But what's the difference between force B and force A? What's the difference between it? Yeah, the magnitude is the same, but what's different about it? Well, take a look at the direction. Take a look at the direction it's going. This force has a y component that goes this way, right? And then it also then has an x component that goes this way. Whereas this force up here had a y component that went this way and an x component that goes this way. Sorry if it's a little bit off. That's okay. So you see what I did there? Look at the y components. Are they pointing in the same direction? Are they? No, they're not, right? This one's pointing up, this one's pointing down. So what's going to happen to those two? Well, here's a hint. This is 43 pounds here, right? Pointing up. and this is 43 pounds here, pointing down. So what's 43 minus 43? It's 0, right? So that means, and let's make a quick little statement here. That means, and I don't have, oh, I do have a sigma. Do I have a sigma? I do. I think I have a sigma in here somewhere. Somewhere. Those are arrows, bullets, clocks, math. There's my sigma, right? That means the sigma Fy equals 0. And why does it equal 0? Because it was 43 plus negative 43. Right? So that means that this boat, is it going to move vertically at all? Yes or no? No, it's not. Okay? The net y force here equals 0. So it's not going to move in the y direction. But now let's take a look at the fx's, right? This one here was 61.4 pounds. This one here is 61.4 pounds. They're both pointing in the right, to the right. If they're both pointing to the right, what's the net force in that direction? Are we going to add those two, or are we going to subtract those two? If they're pointing in the same direction, do they help each other, or do they hurt each other? Another way to look at it, right? If they're pointing in the same direction, does that make it easier for each person to pull the boat? So they'll help each other, right? Yeah, you got it. So 61.4 plus 61.4, that would equal 122.8, got ahead of myself there, pounds, right? So that means that in the x direction, these two vectors complement each other. So I can kind of think of this as, can I drag this? No, it's not going to let me drag it. Okay, I was going to try to drag it and put it over there, right? So these two forces help each other, and then the resulting net x force is 122.8 pounds. And there's no force in the y direction. So what's the final resulting force? The final resulting force, yeah, oops, let me change the color. You got it, right on. 122.8 pounds pointing to the right. So it'd be directly right. So our answer to this problem would be the boat will move with a force of 122.8 pounds to the right. So see how in this problem here we're indicating in our answer two things. And it's important to remember with net force problems. You have to indicate not just the magnitude, but you also have to indicate, you also have to indicate the direction. Okay? So saying 122.8 pounds to the right. Now we lucked out in this problem because there was no vertical change. If there was a vertical change, we would have to take it a little step further, and we're going to do that in the next problem, and you'll see what I'm talking about. Okay? All right. Questions on that problem at this point? Straightforward? Good? All right. Let's take a look at the second problem. Okay? Kind of similar. So here's the second problem. There are two cables that are supporting this. This font's a little small for my class. Let me make this a little bigger. There we go. There are two cables that are supporting a tree. Cable 1 supplies a tension force of 45 newtons directly north. And cable 2 supplies a tension force of 65 newtons directly east. Where must a third cable be placed so that the net force on the tree equals 0? All right, so that's our problem. So we have to figure out where we have to place this cable, and of course, how much tension does it have to supply. All right, so we have a kind of a tricky problem, but not too bad if you think about how to apply the problem, right? Well, here's a question for you. Is the direction that's indicated by this question mark accurate? Is this where a third cable would have to be placed roughly? No. No? You don't think so? Well, roughly, right. We don't know the exact position of it yet, and we don't know how much tension it has to supply yet, but what would it be based on? Yeah, he said the power of the other forces pulling, and that's right. That's exactly right. We would have to figure out what is the net effect of these two forces, and then understand that once we find out what the net effect of those two forces are, then we would have to counter that. So let me kind of draw you a picture here. This force here would somehow cause this force here, right? Let me try that. I'm going to draw that in a different picture, different color, excuse me. That would be something like that, right? Okay? We understand that those two forces combined would kind of have a net effect of that in some direction. We haven't figured that direction out yet, but understand that that's kind of what we're looking for here, right? So if that's the case, that means that we have to place a third cable, and then this third cable would have to be opposite this cable, this resultant, excuse me. All right? So let's figure that out. Well, this is 45 newtons here, this is 65 newtons here. In a problem like this, I like to kind of figure out the a right triangle, because you see that this is pointing directly east and this is pointing directly north. So there's really no components that we have to figure out, because this is all x and this is all y. Right? So I can draw a picture like this. I can say here's 65 newtons here, and I can say here's 45 newtons here, right? And then here's my hypotenuse, or my resultant, right? And this is really, I mean, this in a way is really just a right triangle trigonometry problem in disguise, right? Because if it's 65 here and 45 here, what's a quick and easy way that I can figure out what this is? Starts with a P. Yeah, that's right. Yes, he said the Pythagorean theorem. That's right. So if I just want to do the Pythagorean theorem, and this pretty much would be the quickest way to find out that resultant force. At some point, I'm going to have to use trig, because I'm going to need an angle at some point. But definitely a squared plus b squared equals c squared would work out nicely here, because then you would have to just 45 squared plus 65 squared. And if I square rooted that whole thing, that would equal c, right? So if I just did the square root of this, sqrt of that, right? So I kind of just, you know, square rooted both sides and then plugged in here, right? So let's get my calculator out. And yeah, 45 squared. Now question, will this answer be greater than or less than 65? It'll be greater than. Good. Because what we're going to end up with is we're going to end up with a hypotenuse, right? So if we want to get a hypotenuse, and I'm just going to do the, I'm going to raise this to the 0.5 just because I can't find the square root button. 79 newtons would be our resulting force. All right, so we'd end up with 79 for this problem. Whoops. Drag this here, 79 newtons. Okay, so we could Pythagorize that and get ourselves 79 newtons as our answer. Now, that would be the amount of tension that we would have to get on this cable here, right? So we have to get a little bit of tension on that. 75 newtons would be our magnitude, but where should we place it? Now, for that, we're going to need a little trick. Closer to the 45 newtons? Okay. Then we would place it, so you're saying right-ish here, right? Okay. So, but there's a way we could figure out what that actual angle is, right? If we want to know what this angle is here, if we find this angle here, this is a vertical angle here, and we'd figure out this angle here too, right? Because these are intersecting vertical angles. So if we find this, we can find this. Look back at this diagram. Is there a way to find this angle right here? There is, absolutely, right? This is our adjacent, this is our opposite, excuse me. This is our adjacent, and this is a reference angle. So if I did the tangent of this angle, do I have a theta on this symbol here? No, they didn't give me that. I can go Greek. Here's our theta, all right? Equals, and that would equal the opposite divided by the adjacent, which in this case equals 45 over 65. And if I wanted to find out what the angle is, I can just do the inverse tan. Tan minus 1. Inverse tan of that ratio. And that would equal my theta. All right? So if I go to my calculator, and I can do that here, if I just go to 45 divided by 65, oops, and then I hit the inverse button on my calculator and then do the tangent. This is just a Windows calculator, and I get an angle that's actually pretty close to the angle we had in the other problem, almost 35 degrees. 34.7 degrees would be, whoops, 34.7 degrees would be our angle in this case. Okay, so 34.7 degrees. So there you go. Now that tells you, of course, if this is 34.7 degrees, that means that this cable would have to be placed 34.7 degrees below the westward direction here. So we can say the third cable, for an answer, the third cable needs a tension force of 79 newtons and placed at an angle of 34.7 degrees south of west. Okay, that's how we would kind of describe that. So there you go. That's another example of a net force problem. Okay. Now you can get very complex very fast in these kinds of problems. And we'll do one more problem where we're going to take two forces and we're going to find the net force, but the two forces are going to be placed at kind of odd angles. All right? So here's that problem. So we're going to do this. Okay? Let's say we have an object, like a picture. Let's say it's a picture. All right? Maybe a sign. And it's got two supporting cables. Cable number 1 pointing this way, and cable number 2 is pointing that way. Okay? So this one here, let me place some dashed lines here to get some reference angles here. All right. This cable here is going to be 25 degrees. 25 degrees. And this angle here, let's draw another one of those lines, is going to be 60 degrees. Right? Okay. So again, not quite a right angle, but close to one between the two of them, right? And then let's go ahead and label some magnitudes. We'll say this force right here, this cable, is supplying a 35 Newton force, and this cable is supplying a 25 Newton force. So the question here is going to be, what is the net force? All right. Now, this problem is different than the previous problems because now we have not one but two forces that are not at cardinal directions. They're not directly left, right, up, or down, or west, south, north, west, south, east, or north, right? So that means that because of that, we'd have two forces that each need component forces. They would each need some components. So here's an example here. Whoops, wrong direction. This force would have a x component here and a y component here. And see what I'm doing here is I'm just kind of sketching this out. You should do the same thing when you're drawing these problems in your notebook. You want to draw the component forces often. Let me do a different color for the second force. There we go. That's one. And then there we go. And you want to do that because that will remind you that you need to find the components of these before you can kind of answer the question. So here's our first force here with an Fx and an Fy. And then here's the second force, Fx and Fy. So how do we go about solving this problem? Well, in order to find a net force, we would have to know how much effect each of the forces is having in both x and y directions. Because in order to find the net force, we would have to know what is the net Fx force and what is the net Fy force. So this is the problem. This is probably as complex as they would get. The only way to make a problem like this more complex is to add more forces. But if you do that, that's really not making it, it's not making it harder, it's just making it more time consuming, right? Having like, if you had like 5 forces acting on a point and then had to find the components of all 5 of those forces, it's no different for each force. It's just multiple iterations of the same thing, okay? But ultimately, no matter how many forces you have, you're going to have to find out what is the net force in the x direction and what is the net force in the y direction. So in this problem, let's find out first what are the x forces acting here and how much are they, right? So let's take this 35 Newton force. Now remember, we have a shortcut, okay? We have a nice shortcut. If you have the force value and you want to know what the component force is, say for x example, right? if you want to know what that is, you just got to do F times the cosine of theta. And if you want to know what the y force is, the y component, excuse me, then you would need to do the force times the sine of theta. This is a nice shortcut to have. All right, so that will save you some time. As long as your angles are against the horizontal, these two formulas will always work. Okay? So for this force here, if I just want to find the x component, I just need to do 35 times the cosine of 25. So once you kind of get the hang of the formula, did I close the calculator? I must have closed the calculator. Okay. So once you get the hang of the formula, you just need to plug it in, right? So the force value is 35. The angle is 25. So we just do 35 times the cosine of 25, and we get 31.7. So one of the forces here is 31.7. That's this one right here. And since it's pointing left, I'm going to make it negative. Okay, 31.7 newtons in this case. And then Fy, that's 35 times 25 sine. On my calculator, I have to enter sine after I type the number in. So that's 14.8. And we'll just do tenths. That's fine. 14.8 newtons. All right. So we have it, and that's positive because it's pointing upward. Over here, this force here, 25 newtons this way, 60 degrees. So we'll do the same thing. We'll do 25 times 60 cosine. That's half. That's easy. Half that's 12.5. That's 12.5. And then for the y, we do 25 times 60 sine, and that would be 21.7. Okay. All right. So once we do that, the reason we do that now is because then we can just simply answer this question, which is what is the net fx and what is the net fy? So we're going to just kind of answer the question like this. The forces that are acting in the x direction. Oops, let me turn my subscript back off. The forces that are acting in the x direction. There's two of them, right? There's negative 31.7. Let me expand this. There's negative 31.7. And there's positive 12.5. So the net effect on those two forces, if we combine those, we get negative 18.8, I want to say. Let me make sure. 12.5, 18.8. Yep. No? No, that's not right. Let me take my calculator. 19.2. Okay, that was close. 19.2. All right. So that means the net force in the x direction is negative 19.2 newtons, which means it's pointing to the left, right? And here, with the Fy, again, we have two forces acting in the y direction, okay? They are 14.8 and 21.7. And since they are both pointing upward, we would add those, and the sum of those forces is going to be 36.5 newtons. Okay. Now, in this problem, and like I said, the only way to make this harder is add more forces, but it would still be the same procedure. You would still have to just take each force, get their components, add their components separately to get a net force in each direction. Okay? This is where we have to do something different, though, because you notice that we have a force in the x and we have a force in the y direction. So to get the resultant force, we have to draw what I like to call a resultant triangle. Okay? And here's a resultant triangle. The x forces are pointing to the left. The net x forces are pointing to the left. Okay? So I'm going to draw a vector that points to the left. Like that. The net y forces are positive, which means that the net y forces are pointing up. So I'm going to draw a vector up that starts at the end of the x vector. Right? So this vector here would represent the sum of the forces in the x direction, and this vector here would represent the sum of the forces in the y direction, which we already calculated, right? We already figured this out. We got this is this, and I'm going to use just the magnitudes here, so not the signs. 19.2 here and 36.5 here. Now, the last part of this would be the actual retail resultant vector, which is this one right here. This vector would represent our entire net force. How do we find that net force? What do you think? What do you think we'd have to do? Well, if I have the adjacent value and I have an opposite value, can I use something to find this value here? The answer is yes. I can use the Pythagorean theorem. A squared plus b squared equals c squared. You got it. Okay? And then the same with the previous problem here, right? I just take the a squared plus b squared and square root that. That would give me this net force here. So I'm going to do 19.2 squared plus 36.5 squared. And then I would do the square root of that entire thing. And that will equal the net force. That would equal the net force. Question, go ahead. Okay, yep. Okay, so let's get the calculator out. Now the question here, will the net force be greater than or less than 36.5? My student said it would be greater than, and my student is correct. Because when we take this and we take the square root of it, we should get a value that is greater than the other two vectors. Yeah, that's right. So 41.2 is the net force. So the magnitude of the net force is 41.2 newtons. Now we know right now that that force would be pointing in a northwesterly direction. Okay, I haven't specified. It could be up and right, up and left, excuse me. But again, how do I find out what that angle is? The best way to do that, really the most efficient way to do that, and I'll write a formula for you. The inverse tan of the, I said, sorry, keyboard problems here. Stop it. The net force in the y direction divided by the net force in the x direction. Okay, and why? Because the inverse tangent is opposite over adjacent. So if I did this, that would equal the angle that the resultant force is at. So like I said, this is the most complex of the problems that you would have to do, because you would not only have to find the net force because you have two different components of this, two different sums of this, you would then also have to get the angle that it's at too. So for this, it's going to be 36.5 divided by 19.2, and then I'd have to do the inverse tan of that, and that would be 62.3 degrees. So this angle, so this is not quite an accurate drawing, as you can tell. I made the 19.2 vector greater than the 36.5 vector in my sketch, is what it is. But yeah, 62.3 degrees would be our angle. So our final answer to a problem like this would be the resultant force is 41.2 newtons at 62.3 degrees, and then we'll say up from left. We also could say north of west, right? Those are all possibilities here. We didn't really specify whether we were looking at the top of it or we're looking at the side of it. So that's really what we'd have to say, one of those two things. Okay? All right. Does anybody in the live audience have any questions? All right. Would you say that that's the hardest problem out of the ones? Yes, definitely. This one has the most steps. Okay? But like I said, the more forces you add to this, it's just a matter of having more forces to add. But the ultimate thing, you're still finding the net F forces in the x direction, you're still finding the net F forces in the y direction, and still having to find the resultant F force using this sort of resultant vector setup. Okay? So I hope you enjoyed this video. I hope you learned something. I hope it helps you. If you have any questions, please comment below, and please remember to subscribe to eSIMS Engineering. And if this video helped you learn about net forces, please go ahead and like this video as well. Hope you have a wonderful day. Don't forget to be awesome.